Welcome to another video on module 1. This video mainly focuses on adders, subtractors, as well as arithmetic and logic units. So first off with adders. An adder is a circuit that adds two n-bit operands. That means the n bits, the number of bits. For example, 2 bits, a single bit may be two numbers of n bits, okay, to produce an n-bit result and a carry out signal. So whenever you add binary numbers, for example, we add two binary numbers of a single bit, a and b, okay, if a is 1 and b is 1, when you add them you have an output of 0 and there is a carry bit of 1, okay. So the adders give you an n-bit result as well as a carry out signal. The simplest adding circuit performs addition in much the same way as humans do. Fine. So basically it's from right to left, okay, bit by bit, from the least significant bit to the most significant. There are different types of adders: half adders, full adders, and parallel adders. Fine. Starting with half adders. Starting with a half adder, we can say that half adder is a combinational circuit. All of these circuits that we're studying now are combinational circuits, okay, because they are made with a combination of AND gates or any other gate that is used. The half adder has only two inputs. Fine. They represent 2 bits, okay, to be added, and 2 outputs. One of them will be the sum output and the other is the carry. This is the diagram that is used to represent a half adder. We have inputs A and B. There is a sum and a carry that come as the output. And here is our truth table. So when you add two zeros, you get a 0 in the sum. There is no carry as well. When you add 1 and 0, 0 and 1, the sum is 1. Again, 1 and 0, same, sum is 1. No carry for either of them because there is no bit that is exceeding the limit that sum can hold. Okay. When you add two ones, just as I explained, the sum is 0, but there is a carry of 1. This is a k-map for a 2 variable k-map for the truth table. Now we can recognize the circuit using the following expression. Fine. Over here we can see two different states where the sum is 1, okay, that is a b0, a1 b0 and a0 b1. And for carry we have the following schema where we see there is only one condition: a and b both are 1, okay. So from these two expressions we can finally make a logic diagram, okay. To simplify this, we have used XOR over here. So an XOR gate for a and b gives us the sum, and a and b ANDed together, since we have both a and b have to be 1, we get the carry bit. This is a simple logic circuit for a half adder, the truth table, the k-map, and this is all you need to know about a half adder. Now the full adder is a bigger form of a half adder, okay. It gives the sum of 3 input bits, okay. It consists of 3 inputs and 2 outputs, okay. What are these inputs? So basically it overcomes the limitation of the half adder, okay, which is used to add 2 bits only. Fine. When there are 3 input variables, 8 different input combinations are possible. Hence the full adder has this advantage. This is the truth table. We have inputs a and b plus a third input called carry in, okay, and then we have a sum and carry out. According to the truth tables, we have realized the k-map for the sum and the carry, and according to the variables that we've used, we have derived the Boolean expression from the k-map, which then allows us to make the diagram. Now the diagram may seem confusing, but you can consider this. In order to simplify it, we look at it as a full adder which is made using 2 small half adders, an XOR gate, AND gate, XOR gate, AND gate, plus an extra OR gate. Fine. So the XORing of a and b gives us the sum, fine, and then the XORed output is again XORed along with the carry bit. Fine. So in order to get the sum of half adder, we needed only a single XOR, okay, but since we have 3 variables over here, so the XOR of AB with the XOR of C gives us the final sum. As for the C out, over there we had a single AND gate for A and B, but since we have 3 variables, what we're going to do is we're going to do ANDing for A and B, okay, and the output is going to be ORed with the output of another AND gate, and this AND gate is giving a C in and the XOR value, okay. Just look at this circuit for a while, try to understand. you'll see how simple it is, since it has only two half adders and an extra OR gate with an extra input. Here it is. So you can see one half adder, another half adder, an extra OR gate giving out the sum and carry, two inputs A and B, and an extra carry input. Makes, so these, combining these gives you a final full adder. Now what is a parallel adder? A single full adder performs the addition of two 1-bit numbers. Okay, so we have two 1-bit numbers and an input carry. The difference of a parallel adder is that it is a circuit capable of finding the arithmetic sum of two binary numbers that are greater than 1 bit. So it can carry the sum of n-bit numbers. Fine. A parallel adder is made by full adders connected in a chain. Fine. Where the output from each adder is connected to the input of the next adder. This here is a parallel adder for a 4-bit adder. Okay, so we have A and B, that are two numbers, each is 4 bits. We use full adders. Okay, so for the first 2 bits, 1 bit of A and 1 bit of B, which is A1 B1, we use one full adder. Okay, we give a carry in and we get a sum out with the carry out. The carry out is the carry in for the next full adder, and the next full adder has inputs A2 and B2. Again we get some S2, and we continue so on, chaining it all the way till n. If we have 4 bits, we will have 4 full adders, and the output will be considered from S1, S2, S3 and S4. Again, as we explained, the full adder works by taking the carry input C1. Okay, it generates the sum S1. C2 is generated, which is connected to the next adder in the chain. The next full adder has the bits A2 and B2, and it has the carry out C2. Okay, added from the first adder. It has a sum C2, and then the C3 carry, which is generated from this, goes to the next adder, and so on. Now a subtractor. It is the most essential combinational logic circuit used in digital electronics. So it uses it's as the name states, basic. The subtractor is used to perform subtraction of two binary digits. Okay, they take two numbers as input and subtract one binary number input from the other binary input. Similar to adders, it gives two outputs, difference and borrow. In case of subtractor, we have a difference because adder had sum, so this has difference. In the adder, we had a carry. That means whenever there is an overflow in the digit, it goes to a carry. That means it gets added to the next. In case of subtraction, what happens is when you have subtraction between two bits, the case of underflow takes place. So sometimes the number that is getting subtracted, okay, so A and B is there, B is subtracted from A might be small, okay, hence it needs a bit from the previous number, hence a borrow. Again, subtractors also have three types: half, full and parallel. The half subtractor is a combinational circuit for subtraction of two bits, okay, input X and Y, output D and borrow. Okay, T for difference, B for borrow. The K-map is as follows: A and B, subtracting 0 and 0 gives 0, 0, 1 gives 1 difference. There's a difference of 1, but there's also a borrow because the initial bit is smaller than the bit that is subtracted from it. 1, 0 gives difference of 1, but there is no borrow since 0 is being subtracted from 1. 1, 1 gives 0, and this is the K-map. Hence the Boolean expression and then the realization of the gate. It's the same as half adder, we only add a NOT gate in order to get the difference in borrow. A full subtractor has the same working as that of a full adder. We have inputs A and B, and then we have a borrow in giving us a borrow out and D. So 3 inputs and 2 outputs. Using the K-map, we can make the following circuit. Usually you don't need to study the subtractor circuit, but you can have a look at it and understand how it works for enhancing your understanding of Boolean expressions to make combinational logic circuits. Full adder can also be made using two half adders. Okay, so the same as we realized during the parallel adder. Again, the parallel subtractor can be made in a similar way, OR gate for the borrow, and This is how it's made. A parallel subtractor, on the other hand, just like a full adder, okay, where we use it, the parallel adder, okay, it was used for adding or subtracting n bits, right, two n bit numbers. Over here the difference is we are subtracting two n bit numbers. Okay, so in subtraction the only difference that we get is we use a NOT gate on the input of the b bits. Okay, C in the first carry is set as 1. Okay, so what this helps us to do is the NOT, okay, of b with 1 gives you the 2's complement, and the addition of 2's complement is subtraction. Fine, that's the rule you need to remember. So the addition of 2's complement to a number is subtraction. This is how it works, this is how it functions. The rest of the rules are the same. You get the sum output, you get carry that goes to the next, its carry goes to the next, and so on. Arithmetic logic unit. Okay, the ALU, okay, are found at the core of microprocessors. They implement the arithmetic and logical functions offered by the processor, such as addition, subtraction, ANDing of two values, and so on. Okay, we'll be further discussing these operations. An ALU is a combination circuit that provides common logic circuits in one block. Okay, many common logic circuits in one block. They can they can be designed to perform a variety of different arithmetic and logic functions. Possible functions are given as follows. Okay, we'll be discussing them later on. This is the basic system architecture for an ALU. So the input device is connected to the computer system, which has a memory that transfers data to and from the CPU, and the CPU has an ALU which is connected to control. So these controls are going to help us choose the operation that the ALU is supposed to perform, and then accordingly we get an output. The ALU computes a function of two inputs, so we get two inputs into the ALU, and the output is the result of the two inputs. Okay, the arithmetic operations can be integer addition, multiplication, division. The logical are AND or XOR. This is how the ALU is used to choose which operation is going to be performed. We get two inputs A and B, and any operation needs to be performed in them, whether it's arithmetic or logic. So the system is designed as follows. It gets three control lines, and since there are three lines, there are 8 possible different operations that can be selected. The first 4 represent arithmetic and the second 4 represent logic, or you could shift this. It totally depends upon the person who designs the system. The first 4 could be logical and the other 4 could be arithmetic. We choose the first 4 operations as addition, subtraction, multiplication, division, or AND, NOR, and XOR. Okay, the control units C0 and C1 allow us to select between either this row or this row. What defines the columns, whether it's going to be arithmetic or logic, is the C2 control operation. So when it's 0, all arithmetic operations are selected. When it's 1, all logical operations are selected. So whenever C2 is 1, you cannot get an addition or an arithmetic circuit. Only logical units will be done. Thank you, that's it, and see you in the next video.